Alright, in this video we're going to be talking about combining probabilities. This is section 7b. And here we're going to be focusing on and probabilities. Those are probabilities with the word and included. So an and probability will deal with independent events. Two events are independent if the outcome of one does not affect the probability of the other event. Okay, that's what a independent event is, by definition. So if we have two independent events, A and B, they have individual probabilities. Probability of event A and the probability of event B. The probability that A and B occur together is this. The probability of A and B is equal to the product of the probability of event A and the probability of event B. We're going to multiply those two together. Now that principle can be extended to any number of independent events. So like in this first example here, we're going to determine whether the following individual events are independent or dependent. Then find the probability of the combined event. In this case here, rolling 2 5s followed by 1 on 3 tosses of a fair die. Okay. Now, this is considered to be an independent event because what we get on the first row does not depend upon what we get on the second or the third. So here, we consider that to be independent events. Now let's find out what that probability is. And we're going to give our answer as a simplified fraction. So here, the probability of a 5 or another 5, and another 5. Okay, need to correct that. A 5 and a 5 and a 1. So we're looking at the probability of getting a 5 multiplied by the probability of getting another 5 multiplied by the probability of getting a 1. So here, let's look at the probability of getting a 5. On a single die, there's 6 numbers on a single die. There's only one way of getting a 5, so it will be 1 out of 6 times 1 out of 6 for the probability of getting a 5 again. And for the probability of getting a 1, that's also 1 out of 6, because there's only one 1 on the die. Now we're going to multiply those numerators and denominators together. The numerator will be 1 times 1 times 1, which is 1. The denominator, 6 times 6 is 36, times 6 will be 216. So, in this case here, the probability of that combined event will be 1 out of 216, or 1 over 216. Okay. Now, we also have an and probability when we're dealing with dependent events. Two events are dependent if the outcome of one affects the probability of the other event. The probability that dependent events A and B occur together will be this. The probability of A and B is going to be equal to the probability of A multiplied by the probability of B, given that event A has already happened. So, one will depend upon the other in this case. Now here, this is where probability of B given A is the probability of event B given the occurrence of event A. And this principle can be extended to any number of dependent events. Okay, as soon as I can get this. Alright, now let's look at an example of this. In this case, we're determining whether the following individual events are independent or dependent. Then find the probability of the combined event. In this case here, randomly drawing and immediately eating 2 red pieces of candy in a row from a bag that contains 13 red pieces of candy out of 38 pieces of candy total. Okay. Now, as we can see here, we're going to get a dependent event. Those events are going to be dependent of each other. Okay? So now, we want the probability of getting 2 red pieces of candy. So on the first choice, the probability of getting a red candy, notice there are 13 red pieces of candy out of 38. So the probability of getting the first one will be 13 out of 38. Now, if we get a red candy on the first selection, and then on the second selection, we get a red candy, the number of pieces of red candy will decrease by 1, and the total number of pieces of candy will also decrease by 1. That's why it's a dependent event, because now on the second choice, you're only going to have 12 red candies instead of 13, and then you're going to be left with 37 pieces of candy total altogether. Now, they want this as a decimal rounded to 3 places. In this case here, let's do this. I'm putting a 13 over 38 in parentheses, so it'll be left parentheses, 13 divided by 38, and then I'm going to close the parentheses. Let me clear that out. Now, here we go. Left parentheses, 13 divided by 38. Close parentheses. Then that's going to be multiplied by, left parentheses, 12 divided by 37. Close parentheses, and then hit enter. Now the 3 decimal places, this 0 is a third number after the decimal point. The number to the right of it is a 9. That's bigger than 5, so we increase that 0 to a 1. So this will be 0.111. That would be the probability of eating 2 red pieces of candy in a row from a bag that contains 13 red pieces of candy out of 38 pieces of candy total. Okay, now this next example, here we're going to determine whether the following individual events are independent or dependent. Then find the probability of the combined event. Here we're randomly selecting a 4-person committee consisting entirely of women from a pool of 11 men and 15 women. Okay. If we look at that, if we're going to select a 4-person committee, that means the number of people we have will be decreasing. So here, we're going to have a dependent event as well. So now, let's find out what the probability of selecting a 4-person committee. Excuse me. The probability of a 4-woman committee. A committee with 4 women only. Okay? So now, the first one we select, there are 15 women that we can select. Out of, if we add 11 and 15 together, you're going to get 26 people altogether. Then we're going to multiply that by, now the second one we select, we're going to be down to actually 14 women. And instead of 26 that we're going to be choosing out of 25. And then multiply, the third one we select, instead of 15 women, we've already selected 2, so we're going to be down to 13. And instead of 25, we're going to be down to 24. You kind of see where the pattern is going here when we're dealing with dependent events here. Alright, and then that 4th woman that we chose, we're going to be choosing 12 women. Instead of out of 24, it'll be out of 23. Okay, so now let's find out what that decimal value is to 4 places. Okay. So now I'm going to do left parentheses 15 divided by 26. Close parentheses. Notice I'm putting the fractions in parentheses here. And then times parentheses 14 divided by 25. Parentheses times left parentheses 13 divided by 24. Right parentheses times, and then left parentheses again, 12 divided by 23. Then hit enter. Now the 4 decimal places, the 4th number after the decimal point is the 3. To the right of it is 0. That's less than 5, so we leave that as 0.0913. Okay. That represents the probability of randomly selecting a 4-person committee consisting entirely of women from a pool of 11 men and 15 women. Okay. Alright, next we're going to look at either or probabilities. And these are non-overlapping events. 2 events are non-overlapping if they cannot occur together, like the outcomes of a coin toss as shown to the right. Well, outcomes of a coin toss. Now, for non-overlapping events A and B, the probability that either A or B occurs is shown below. Here, the probability of A or B will be equal to the probability of event A plus the probability of event B. Now this principle can be extended to any number of non-overlapping events. Okay. So like in this example that I'm going to show you, example 4, determine whether the following individual events are overlapping or non-overlapping. Then find the probability of the combined event. Okay, getting the sum of either 2, 8, or 12 on a roll of 2 dice. So it's either getting a sum of either 2, 8, or 12 on a roll of 2 dice. And in this case here, those 2 events will be non-overlapping. Okay. And now we want to find that probability of that combined event. So, if I want the probability of a 2, or an 8, or 12, that means I need the probability of getting a 2, excuse me, plus the probability of getting an 8, plus the probability of getting 12. Alright, now we got to think of this. We're dealing with 2 dice. What will be the probability of getting a 2? There's only one way you can get a 2, and that's a 1 and a 1 on 2 dice. So here, that probability will be 1 out of, and if you recall on the last video that I did, where I showed you all the outcomes for 2 dice, there were like 36 possible outcomes here. So it's 1 over 36. The 36 come from the fact that on one die there's 6 possibilities, on the second die there's 6 possibilities. So if you multiply 6 times 6, you're going to get 36. Plus, The probability of getting an 8. Well, you got to think of this. There are 5 possibilities. A 2 and a 6, 3 and a 5, 4 and a 4, 5 and a 3, 6 and 2. And that's out of the total of 36. Plus, the probability of getting a 12. There's only one way you can get a 12, will have to be 6 and 6. That's it. So that's one possibility out of 36. Now let's add those 3 probabilities together. Here the denominators are the same. I can add the numerators. 1 plus 5 is 6, plus 1 is 7. So, the probability of that combined event will be 7 out of 36. Okay, and you might want to check out that video for section 7A, because I did show you that table with the probabilities for all the outcomes for rolling 2 fair dice. Okay, let's say we had overlapping events here. Your either or probabilities could have overlapping events. That means one could be common in both A and B. Here, 2 events are overlapping if they can occur together, like the outcome of picking a queen and or club, as shown. Well, I'll do an example just like this one. For overlapping events A and B, the probability that either A and B occurs is shown below. So here the probability of A or B, that's equivalent to the probability of event A added to the probability of event B minus the probability of A and B occurring. That probability represents the overlap. Okay. So in this case here, if I was to draw a Venn diagram, and this is what a Venn diagram here looks like, a box with circles in it. That's A. This will be A, and this will be B. This shaded area in red represents A and B. That's the overlap. What they have, what's in common in both A and B. Okay. Now this principle can be extended to any number of overlapping events. Okay, let's look at example 5. Determine whether the following individual events are overlapping or non-overlapping. Then find the probability of the combined event. So here let's say we had this. Drawing either a spade or a club from a regular deck of cards. I want to find that probability. Okay. Now, spade, there are 13 possibilities for a spade. And then you got clubs. That's also 13 possibility of a club. There are 4 suits. Those suits are independent of each other, so we don't have to worry about an overlap in those 2. So here, this is considered to be a non-overlapping event. So now the probability of a spade or club is this. The probability of getting a spade added to the probability of getting a club. Now we don't have to do the minus the probability of a spade and a club because there's nothing in common for those 2. Because those 4 suits have nothing in common to each other. Now, as I stated earlier, there are 13 cards that are spades out of 52. So this is 13 out of 52 for the probability of getting a spade. The clubs also has 13 cards with clubs in it out of 52. Now if I add 13 over 52 to 13 over 52, I get 26 over 52. And if I reduce 26 over 52, that's going to end up being 1/2. So the probability of getting a spade or a club would be 1/2. Okay, and I do regret by not giving you a event where it was overlapping. Now, let me do the one that was overlapping. Let's say we have the probability of getting a queen or a club. This would be considered a overlapping event because if you look at it, there are 13 queens in the deck of 52 cards. But the clubs also has 13 clubs in a deck of 52 cards. However, there's an overlap. We do have a queen of clubs. Okay? So here, we have to do this. The probability of getting a queen plus the probability of getting a club. And then we got to subtract from it that overlap. We got to subtract that overlap of the probability of getting a queen and a club. So here the probability of getting a queen, in this case, was 13. Actually, there are 4 queens. 4 out of 52. There are 4 queens. Because you got the queen of club, queen of hearts, queen of diamond, and queen of spade. Alright, the number of clubs, there are 13 of those out of 52. Now let's subtract out that overlap. There's only one queen of clubs, a queen and a club, so there's only one queen of clubs out of 52. Alright, now add and subtract that. 4 plus 13 is 17. 17 minus 1 will be 16 over 52. Let's see, if we divide the numerator and the denominator by 4, because that's the largest number that can go into 16 and 52, this will end up being 4 over 13. So the probability of getting a queen or a club with this overlapping event would be 4 over 13. Alright. Now next we'll look at the at least once rule. Okay. I think that's the last thing we'll cover in this video. The at least once rule for independent events. Suppose the probability of an event A occurring in one trial is P of A, as indicated here. And if all the trials are independent, the probability that event A occurs at least once in trials, in number of trials, that's going to be shown below here. The probability of at least one event A in n number of trials, that's going to be this. 1 minus the probability of not getting an A, of not getting event A in n trials, or 1 minus the probability of not getting an A, and that part is going to be raised to the power of n, where n is the number of trials. Okay. Excuse me. Alright, now let's look at example 6, how we can use that particular formula to get that particular probability. Here we're going to use the at least once rule to find the probabilities of the following events. That is, getting at least one head when tossing 4 fair coins. Okay? So here I want the probability of at least one head in 4 trials. Okay, so in this case here, that's going to be, now keep in mind, at least and no are complements of each other. They're opposites of each other, as we talked about in the last video section 7a. So I have to do 1 minus the probability of getting no heads in 4 trials. And that would be like saying 1 minus, and in this case, the probability of not getting a head. And that value is going to be raised to the n, which is the number of trials, and in this case, it's going to be raised to the 4th power. Okay, now let's think about this for a moment. The probability of getting a head on a single coin toss is 1/2. The probability of not getting a head, that's 1 minus the probability of getting a head. That's 1 minus 1/2, which is, of course, 1/2. So now I have 1 minus. The probability of getting no heads would be 1/2. That's going to be raised to the 4th power. Let's see, they want this as a simplified fraction. So if I do 1/2 raised to the 4th power, that means I need to raise the numerator to the 4th power and raise the denominator to the 4th power as well. So if I do 1 to the 4th power, that's going to be 1 over 2 to the 4th is 2 times 2 times 2 times 2, which is 16. And you can do that in the calculator if you want to. 2 and then the hat key, which is right here for your exponent, and then 4. That gives you 16. And let's do 1 minus 1 over 16. 1 minus 1 divided by 16. That's this. But for a fraction, we have to press the math key and select number 1 for fraction. This will give you 15 over 16. So, in this case here, the probability in this case will be 15 over 16. That's the probability of getting at least one head when tossing 4 fair coins. Alright, let's look at the next example here. Use the at least once rule to find the probability of the following event. Here we're getting rain at least once in 4 days if the probability of rain on each single day is 0.2. So if the probability of getting rain is 0.2, the probability of not getting rain, that's going to be 1 minus 0.2. And 1 minus 0.2 would be 0.8. Okay. So now let's find the probability of getting rain at least once in 4 days. That's going to be this. We have to use that rule that says 1 minus the probability of no rain in 4 days, which is equivalent to 1 minus the probability of, I'll put that in bracket, no rain. And that's going to be raised to the 4th power because that's the number of trials here in 4 days. So now we do 1 minus the probability of no rain. That's 0.8. That's going to be raised to the 4th power. Now in the calculator we're going to do 1 minus we're going to do 1 minus, let's see, 0.8, then the hat key for the exponent, and then press number 4. Delete that. And to 3 decimal places, this will be 0.590. Okay, that represents the probability of getting rain at least once in 4 days. So make sure you round up to the number of decimal places that the homework specifies. Okay? Okay, and here's the last example in this video. Again, we're going to use the at least once rule to find the probability of getting at least 1/6 in 3 rows of a single fair die. Okay, so in a single fair die, the probability of getting a 6 is going to be 1 out of 6, because there's only 1/6 on a single die. That means the probability of not getting a 6 is going to be 1 minus the probability of getting a 6, which means we got to do 1 minus 1 over 6. And again, I'll do this on the calculator in case you need to know how to enter fractions. 1 minus 1 divided by 6. That gives us the decimal. Hit the math key and then select number 1 for fraction. That gives you 5 over 6. So the probability of not getting a 6 will be 5 over 6. So now we can use that at least once rule, where the probability of getting at least 1/6 in 3 rows, and that's going to be equal to 1 minus the probability of no 6 in 3 rows. And that's equivalent to 1 minus this, the probability of no 6. And that's going to be raised to the power of 3, because that's n is the number of trials, according to that at least once rule. So now we got 1 minus. The probability of not getting a 6 will be 5 over 6. So it'll be 1 minus 5 over 6. That's going to be to the 3rd power. Now in that problem, we're going to round to 3 decimal places as needed in this case. So here's how we enter that in. 1 minus, now I'm going to put my left parentheses here. 5 divided by 6, close parentheses. This has to be raised to the 3rd power, so I'm going to hit that hat key for the exponent, and then 3. Then I can hit enter. Now, to 3 decimal places, the 1 is the 3rd number after the decimal point. To the right of it is a 2. It's less than 5, so that 1 remains the same. So it'll be 0.421. And that decimal value is the probability of getting at least 1/6 in 3 rows on a single fair die. Okay. And that will conclude this video on combining probabilities.